Alright, good afternoon. My name is Major Derek Worth, and welcome to my dissertation defense titled Machine Visual Perception for Autonomous Docking Maneuvers. This is a brief overview. In the introduction, I will share my research problem, or my problem statement, and my research objectives. Then I'll dive into what has already been done in the field in the lit review. My research has been split into two major studies. In study one, I'll share my proposed solution to the autonomous docking problem and how I validated it in simulation. Then we'll jump over to study two, where I transition the solution into the real world using transfer learning. And then finally, we'll look at some conclusions and some exciting doors that this work is starting to open. So as my title suggests, the problem I'm trying to solve is autonomous docking, and how I'm doing it is through visual perception. So what do these terms mean? In the context of this work, autonomous docking is the approach, contact, and connection between two vehicles without human intervention, while visual perception is the intelligent interpretation of what is seen. So what I'm trying to do here is give machines visual perception, just like we as humans have. But first, why is all this important? Well, turns out autonomous vehicles are popping up everywhere. Whether we realize it or not, we all rely upon them in our everyday lives, either directly or indirectly. So here's just a few examples. In the commercial sector, we have autonomous vehicles vacuuming our carpets. If you've been to Sam's Club lately, you've seen this guy wandering the aisles, scrubbing the floors. We're seeing them pop up in commercial transportation and delivery services. On the industrial side, we're seeing autonomous freight, mining and excavation, agriculture, and if you've purchased anything on Amazon, your 2-day shipping is made possible by these guys. In the defense sector, we're starting to see them in air, space, land, and sea, and that's just touching the surface. But there's a problem. Despite their growing presence, autonomous vehicles are limited in their ability to interact with each other and their surroundings. Without autonomous docking, they cannot perform complex tasks such as docking for maintenance and crew transfer in space, transferring cargo, passengers, or data at sea, or refueling mid-air. These limitations hinder their operational range, endurance, and effectiveness. Autonomous docking, once solved, overcomes these barriers and significantly enhances their operational efficiencies. In this work, I focus on the aerial refueling use case because of its complexity. On a scale of very difficult to super easy, this task is right at the top. And so the idea here is if I can solve this really hard problem, then I also solve the rest. But I know what you're thinking. Humans already perform these complex maneuvers. So if it's not broke, why fix it? Well, it turns out us humans are very expensive. We require long training pipelines, we have physical requirements, we make mistakes, and eventually we get old and have to retire, many times taking with us years or even decades of experience. So my solution is to completely remove the human from the loop and mitigating all these factors, and this is how I do it. My solution is motivated by how humans perform complex docking maneuvers. That is, by using their visual perception, as you see here, along with their hand-eye coordination. In this work, I replaced the human perception with computer vision and machine learning to enable machine hand-eye coordination. Thus, my problem statement is to develop an algorithm that is accurate, reliable, and fast enough to solve the autonomous docking problem, specifically such that it has high performance and generalizes well across real-world operating conditions. So, what has already been done in this field? I'll begin by answering why computer vision is necessary. We'll take a look at the limitations of traditional analytical approaches, how machine learning overcomes these limitations but requires massive training data sets. We'll then explore the trade-offs between manual and automated annotation techniques, how transfer learning on synthetic images shows promise. Then we'll look at recent work here at AFIT that my research built upon. So why vision? Across the literature, most common relative navigation solutions rely on one or more of these techniques. So at the top, you have your inertial sensors, which are used to measure specific forces, angular rates, and sometimes magnetic fields surrounding the sensor. These are often combined with signals-based approaches like GPS for accurate positioning. In contrast, vision sensors, they extract spatial information for imagery. Of the three, vision is the only one impervious to spoofing, interference, jamming, and drift, making it ideal for autonomous docking. Here are some common vision solutions that produce three-dimensional data, such as 3D point clouds, which in turn must be fit to known models using algorithms like the iterative closest point algorithm. The problem with these approaches is that they are often computationally expensive and slow, require complex calibrations, and produce unreliable predictions. In contrast, monocular vision takes advantage of the camera pinhole model, as you see at the bottom, aligning 2D image points to 3D projections. This method follows a four-step process where an image is captured, 2D features in the image are found, and a correspondence is made with the 3D features on the object, which are then converted into a pose estimate, which with methods such as the perspective endpoint algorithm. So just real quick, I just want to clarify that pose in this work is the combination of position, XYZ, with orientation, yaw, pitch, and roll. So anytime I say pose, I mean all 6 degrees of freedom there. The problem with this four-step approach is that in step 2, traditional feature detection methods are unreliable and do not generalize well across varying lighting conditions. In other words, step 2 is very hard. For example, here are some analytical methods commonly used in step 2. These methods are capable of accurate 2D feature detection, but fail when encountering significant changes in lighting conditions, such as glare, shadows, and poor visibility. Additionally, they require separate 2D to 3D feature matching algorithms like the one shown here, which are also unreliable in varied conditions. What we need is a method that generalizes. So what do I mean by generalization? I've got an example. If I teach my 3-year-old son that this is a bunny, then I show him these pictures, he will say that these are all bunnies. Analytical methods cannot make this jump, and this is where machine learning comes in. Several solutions have been proposed over the past decade, including the one shown here. These combine step 2 through 4, that is feature detection, matching, and pose estimation, into a single network architecture. Reported results are promising, but the major limitation here is that they all heavily rely upon large, expensive training data sets. For example, all those approaches on the previous slide were validated using popular pre-labeled data sets like the one shown here. Unfortunately, these do not translate to real operating conditions and real docking scenarios. To date, methods are limited for generating accurately labeled training data specific to autonomous docking. So 2 types of labeling methods exist. First, there's manual labeling, which requires software like this. Unfortunately, there is also a trade space, and high quality comes at a substantial cost. For example, the 328,000 images from the popular MS COCO dataset that we saw in the bottom left of the previous slide, they require over 30,000 worker hours. To put that in perspective, that's equivalent to one person working full-time for nearly 15 years. Current automated techniques are limited as well. For example, in 2019, Kyokawa used fiducial markers to automate labeling. Unfortunately, since the fiducial markers are always present in the training data, models confuse the markers as part of the object. And in 2021, Homarkivist experimented with label interpolation in time series imagery, where a human labeled every 20 or so images, and then he interpolated the labels in between the images. But unfortunately, his results showed that there was a decrease in model performance. One technique showing a lot of potential is the use of transfer learning from synthetic imagery. For example, Hattori successfully trained models to find real pedestrians from synthetic imagery alone, whereas Pura did the same with items in a refrigerator, and then another researcher performed similar experiments with drones. This last one was really interesting because he also included motion blur and random noise, which increased model performance and generalization. In 2022, an AFIT student defended his thesis on combining the You Only Look Once algorithm with perspective endpoint. He was the first to apply all this to aerial refueling. His results were astonishing because he showed not only could he accurately estimate a pose, but the solution also generalized well and was resilient to occlusions. Following his work, another student attempted the same method on satellites. Though simulation results were promising in both efforts, real-world results were lacking, and that is where my work comes in. Standing on the shoulders of giants, I extend their work to a working real-world solution that I call relative vectoring using dual object detection. Given only the image on the left, the machine can now intelligently determine where the drogue is relative to the probe. So next, we're going to look at study 1 to see how I made all this possible. In this first study, I introduced relative vectoring using dual object detection. I'll explain how it works and how I evaluated in Monte Carlo simulation. I'll also show test results and summarize my findings. My contributions for this study include a novel machine learning technique for finding 3D points in 2D images, a novel vision-based vectoring technique for accurate, reliable, and real-time relative navigation between two objects, and a simulation framework for developing and testing the relative vectoring technique, which includes automation of label training data for machine learning. As we saw earlier, the 4-step process shown here is common throughout the literature. Unfortunately, this is only a half solution. Take this for example. In this scenario, we have a receiver, a Learjet coming in for refueling, and we have a camera attached to the tanker pod looking back. Now, if that camera takes this picture, and then we follow the 4-step process to get a pose of that drogue, that pose is defined in the local reference frame of the camera, which is great if we're trying to navigate the camera into the drogue. But that's not what we're trying to do here. We're trying to navigate the probe into the drogue. So what I propose to make this more useful is to perform this process a second time on a second object, hence dual object detection. Then I add a 5th step that converts the resulting poses into a relative vector. This provides a more complete solution. Dual object detection provides a significant advantage. That is, the camera can be placed anywhere and in any orientation, including sideways or upside down, and as long as the two objects are in the same image, this pipeline will produce the same vector. This means there's no need for extrinsic camera calibrations. So next, I'm going to use that video to explain in detail how the relative vectoring pipeline works. All right. So let's begin with the current method. So on the left, I'm just going to pause it. On the left, you see that using the image in the bottom right, analytical solutions can find features and do the 4-step process to find the camera to drogue vector. And if you know that red vector, the precise probe offset, then you could just do some vector math, and that gives you your probe to drogue vector. But what happens if that camera changes? Say a maintenance technician bumps it, or or turbulence causes that camera to shift. You lose that probe to drogue vector. So what I'm proposing here on the right is that we move the camera to a position that sees both the probe and the drogue, and then you can perform that process twice, and then if you find the vector between those, you get that same exact probe to drogue vector, all the while not needing any extrinsic camera calibrations. All right, so I'm going to skip forward. Here I'm applying the process in Monte Carlo simulation, where the scenario includes a receiver aircraft flying multiple approaches behind the tanker. As shown here, I mounted several virtual cameras on both the receiver and the tanker. In this effort, I report results from 3 vantage points. That's the wing cam, dash cam, and tanker pod cam. The bottom right viewport displays the output of these cameras, which the pipeline uses for relative vectoring. Enlarging the viewport port for just a moment, you'll see that the highlighted features in yellow are the features that we want the network to find. With the blue points, the network is actually finding. These blue points are then transformed into a probe-to-drogue vector using a technique I'm about to show you. So to reveal what's happening under the hood, let's take a look at this diagram. Within this pipeline, I use YOLO version 5 with a novel supervised machine learning method for specific 2D feature point finding. But I'll go more into how we do that in a bit. For now, let's just focus on the pipeline and see how it works. So model point matching is fairly straightforward. Since YOLO also predicts class IDs, I pass these matches to prospective endpoint, which then uses these on the top left to align the three-dimensional model for pose estimation. The resulting pose estimates include a pair of rotation matrices and translation vectors defined relative to the camera. Then I subtract a camera frame probe vector from the camera frame drogue vector, which gives us a camera frame probe to drogue vector. I then rotate this vector into the receiver's local reference frame by multiplying it by the transpose of the probe's estimated rotation matrix. The end result is a receiver frame probe to drogue vector that an autonomous agent can use to navigate aerial refueling approaches. Alright, next in this demonstration, I turn off YOLO predictions and replace them with true 2D image points with 0 pixel error. The pipeline produces sub-millimeter accuracy at even when over 120 meters out. So if I add random noise, as you can see by the yellow circles vibrating, we see that error in those probe drogue vectors increases with the random noise. And this tells us that the 2D feature detection is the most important step of this pipeline. So I accomplish point detection in this pipeline using YOLO, a state-of-the-art object detector. However, the problem with using its traditional bounding box, as we see on the right, is that the perceived 2D object center projected into the image is rarely the same as that bounding box center. This is due to what I refer to as the parallax effect, which is caused by the disparity in projective geometry between points closer to the camera's image plane and those further away. To visualize this effect, let's take a look at this 2D square floating in 3D space. When I form the tightest fitting bounding box around it, the only time we see the alignment between the true center, that's the blue dot, and the perceived center, that's the yellow dot, are when the camera's image plane is parallel to that of the square. Any rotation of either the camera or the square causes the perceived and true centers to diverge. To overcome this effect, I proposed bounding box corrections, such that I grow two adjacent sides of the tightest fitting bounding box until its center aligns with the projection of the 3D truth center. So the blue box is what I trained YOLO with. To automate this process within the pipeline, I define features by selecting 3D points across the surface of an object and use the geometric center of each corresponding point cloud as the 3D feature center. I apply our bounding box corrections to the point clouds as shown here and save the bounding boxes with the corresponding images to file. So I just want to pause here for a second and point out that MS COCO data set that we saw earlier took 15 years for a human working full-time. This process now takes that same data set and reduces the time to produce it to less than half a day. All right, so what I'm showing here is that I also add scene augmentation techniques where I change the background, the lighting, perspective, and this results in better model performance and generalization. So after I train our models from labeled images with bounding box corrections applied, I observed YOLO was able to find 2D points with enough precision for the probe-to-drogue vectoring. Here, I also demonstrate the pipeline does not rely on extrinsic camera calibrations. Shifts in the camera position and orientation do not affect the pipeline predictions. To quantitatively assess the pipeline performance, I collected millions of observations over tens of thousands of random Monte Carlo approaches, comparing truth to pipeline predictions. I found that by switching between multiple models specifically trained on different phases of the approach, the pipeline could navigate the probe to the drogue with high accuracy, reliability, and speed from 120 meters out. Overall results showed that the relative vectoring pipeline is resilient to occlusions, does not require any extrinsic camera calibrations, is reliable and consistently accurate to within 3 centimeters at contact, and runs at least 45.5 frames per second, making it suitable for autonomous aerial refueling. Alright, so that shows how the pipeline works. Now, before we jump into the final results, I just want to clarify that the evaluation criteria is accuracy, reliability, and speed, because that's, again, what I said at the beginning would make autonomous docking possible. So accuracy is defined here as the magnitude difference in Euclidean distance between the truth and prediction vectors. Reliability is the valid predictions made divided by the number of predictions attempted. And then lastly, the speed is just the time between predictions. So here are the final results. I trained several models, but of the 3, these are my top 3 performers. We have 3 here. The one all the way to the left is a probe to tanker model. So it looks for features on the tanker, while the other 2 on the right look for features on the drogue. And this is important because on the approach, when you're 120 meters out, the drogue is too small to see. So finding features on the tanker guides you to the tanker, but also once you get close enough to localize the drogue and make contact with the drogue, you also need another model that's looking at the tanker so that you can maintain echelon formation. So real quick, I'm just going to look at I'm going to show some really interesting results in this close-up of what this model is seeing. We're seeing that there are actually 2 features that are on the tanker's left wing that the network still finds, even though they're completely occluded. So what does that look like? Quick video. So again, look at the features D12 and D13 in the middle. And you'll see them on the left wing of the tanker. You're going to see them disappear. And indicated in blue shows that the network is still finding those features, and very accurately so, despite them being completely occluded. So that was a really interesting observation. Let's see, and then the error plot. So below the picture here, what we see is that the error plots, they converge pretty much to 0 in the X, Y, and Z dimensions, with contact being all the way to the right and then out to 120 meters all the way to the left. So this shows that we can navigate to the tanker. But once we get close to the drogue, how do we dock into that drogue? So what you see on the right 2 plots are models that were specifically trained to find features on the drogue. So this is the pod cam looking back. It's finding features on the drogue consistently and accurately. And then this is the dash cam looking forward, and it's also finding features on the drogue accurately and consistently. And so what we see by the plots down below is that using these 2 cameras, these 2 vantage points, we have enough reliability from 20 meters out up to contact in that middle plot in order to guide the probe close to the drogue. But then the final 12 or so meters, we can use an even better vantage point, and that's that dash cam on the right, and get even more accurate probe-to-drogue vectoring, which allows us to actually make the contact. So at the bottom, you see that the reliability for that middle plot is 100% all the way across. For the wing cam, you see it struggling a little bit, 80% around 120 meters out, but then as soon as you're about 100 meters out, 100% reliability for the entire approach. And then that dash cam all the way to the right, reliability is not very great after 100 or 12.5 meters out, and that's due to the camera's field of view. You've got a wider field of view, meaning that drogue is occupying fewer pixels further out, and that's why you see the error increasing so rapidly. And then just as a sneak peek, comparison between the real results that I captured within this motion capture room on real imagery is shown here in the middle, and as you can see, the results are very similar. So real world imagery with validated with motion capture truth, the plots look very similar to what we're seeing in simulation, which gives us high confidence that this is going to work in real world scenarios. So that was accuracy and reliability. Now we're going to look at speed. For speed, I saw that the pipeline running on the laptop in the bottom left produced prediction at about 22 milliseconds, which is 45.5 frames per second when parallelized. But if you also include the image capture and the remainder of the pipeline, it totaled to about 41 milliseconds total, which in 41 milliseconds using real flight test data provided by NavAir, that's the plot in the top right, we see that the drogue we can expect to move at most about 2.5 centimeters in that time. So that's additional error that is associated with latency, and if you add that to our error associated with accuracy from the previous slide, that equates to less than 6 centimeters of error, which is indicated by that yellow circle in the bottom right. So if we can get in that yellow circle, which I'm essentially showing that we can, that's plenty of margin for getting it inside the 32.5 centimeter radius drogue. So to summarize study 1, I introduced a novel, intelligent computer vision pipeline called relative vectoring. We saw that this is a 5-stage pipeline that uses YOLO to perform feature detection and matching and perspective endpoint for pose estimation. It takes advantage of dual object detection to predict the pose of 2 objects in the same image. Resulting dual pose predictions are then transformed into a relative vector that guides the probe to the drogue. Finally, through Monte Carlo simulation, we saw that it's accurate, reliable, and fast. The study was published earlier this year in the Journal of Neural Computing and Applications with a patent pending for the underlying architecture. All right, next I will discuss study 2, where I use transfer learning to transition relative vectoring into the real world. So in this study, I will share some novel labeling techniques that I came up with, as well as scene augmentation techniques that allow the models to generalize and have high performance. In my experiments, I will show that I both validate performance and generalization in quantitatively here in the motion capture room, but also qualitatively through real flight test results. We'll go over some results, and then at the end I'll summarize my findings. My contributions in this study include a novel method for performing digital twin alignment for machine vision using fiducial targets and motion capture data. A novel, cost-efficient annotation automation technique for rapidly generating realistic and precisely labeled YOLO training data. A novel augmented reality and scene augmentation or set of techniques, augmentation techniques that increase YOLO model generalization and performance, and proven YOLO models that can consistently and accurately find 3D points in real 2D images through machine transfer learning on synthetic data. So how do I get there? This is the overall roadmap I followed. So starting from the top, going to the bottom, scene augmentation, there are 3 attributes that change in any scene. Whether you're watching a movie, walking down the street, or flying aerial refueling missions, the 3 things that change are your background, your lighting, and perspective. So those are the things that I change in the imagery that I generate. The types of imagery, or the sources of imagery that I generate, come from the virtual world on the left, like I showed in study 1, but this time instead of using a artistically generated model, as you see in the bottom left, that you can find on websites like TurboSquid, I actually used a high-resolution 3D model that I used a 3D scanner to generate. So that's the virtual imagery. On the right, we see that I generate real imagery as well inside this motion capture room using real objects, and I use a digital twin alignment in order to do the labeling. And then finally, I merge the virtual and real imagery into a hybrid data set using augmented reality. I then take these images using novel labeling methods. I label them, I train a variety of models, and then I test them test the models on real imagery, including both imagery collected in this motion capture room as well as imagery on real flight tests to validate its performance and generalization. So here are the experimental objects I used. I had a full-scale probe and drogue that I procured from CalSpan. The camera, or the vision sensor I use, is there in the middle with the yellow on it. That's the LVM G5 811C. I performed digital twin alignment using real or using 3D scanned models. So I used that Artec Leo 3D scanner. It's a high-end professional grade 3D scanner that gets real accurate geometry and texture, as you see in the bottom right. And then here I'm going to jump into my labeling techniques. So the first labeling technique I use is motion capture reprojection labeling. In this case, I use, again, real imagery. So I'm capturing an image using that camera that's mounted on the back of the nose cone. And then while I'm capturing imagery, I'm also capturing motion capture data of all those April tags that you see throughout the scene. Those April tags I can then localize or find really fast in the imagery using the April tag software. And then if I have a 2D to 3D correspondence, I can localize the camera and do the reprojections. So let's look what that looks like. I've got a diagram here that kind of helps visualize what I mean by all of that. So in the top left, I have a camera that captures that image. In the top middle, I use April tag software to find the center of each of those tags in the image. So that gives me my 2D image points. And then here on the center left, I'm just going to zoom in. So on the left is how I find those. The April tag software finds the corners of the April tags, and then I just do a diagonal through the corners in order to find the center. Those centers correspond to a physical location relative to those reflective balls at the top, which the motion capture system is able to tell me precisely where those yellow crosshairs are in 3-dimensional space. So with the motion capture data, I get 3-dimensional points. With the April tag software, I get 2-dimensional points. And then if you just follow the yellow paths from left to right, you'll see that I pass those into solve perspective endpoint. That results or outputs a rotation and translation that I can then use to project world space points that are in the motion capture room or the digital twin virtual world into that image, and then get very accurate projections. So how does that look like? Here's some of my initial experiments. So I use the numbered tags to localize the camera, and after the camera's been localized, I get that rotation translation vector from perspective endpoint. Then I can project points, and that's what you see in red. And as you can see, they line up precisely with features like the corner of rivet lines and just bolts and points throughout that image. So this is great. If I can do these feature projections, then I can do the labeling. All right, so next we're going to look at this video to show how this all works. So in the left there, you see the fiducial targets. On the right, you see the 3D data reported by the motion capture system. And what you just saw there was the digital twin alignment. So we take the 2D and 3D points, throw them through solve perspective endpoint, and then that localizes the camera. As long as that camera doesn't move, we have a valid digital twin alignment. Then I can replace the April tags with a real object, that is the drogue, there you see, and then I can project features on the drogue, as we see there, by various colors. Each color represents a different feature on that drogue, and then I can project those into real imagery, as we see on the left. And again, those are feature points that those are defined in the drogue's local space, and then I transform those into world space using the motion capture data, and then now I can project those into the imagery. So I'm going to hide the April tags in the digital twin alignment so that we can focus on the features. So on the right, I have the feature, I project it into the image. On the left, and then so those are features 0 through 64, so 65 features total. And then I can take those features and then do the bounding box corrections with tightest forming bounding box around them. And these become the labels that I train a neural network with. And then I'm just going to fast forward, and then so what we see here is that I can enable all the features, and then by moving the object around, that's perspective. I'm shining light on the drogue, that's lighting, and then we'll see here in a little bit I can also apply augmented reality for background changes. Alright, so that was the first labeling technique. The second labeling technique is manual reusable labeling. And in this technique, so I guess the question I ran into is, why don't I just use the first technique to label images of the probe? So what we saw previously was those were drogue images, and it turns out if I do apply this to the probe as well, it turns out that there is some jitter in the foreground. So as I'm moving the camera around, you see that those features, let's see if I can just pause it right here. Let's see right here. Like, for example, the green feature in the top left of the dashboard of that probe in the foreground is not centered on the actual wooden board. And these features, as I push play here, you see them, they're just kind of hopping around. And this is due to the fact that the model, the camera pinhole model with the intrinsic camera calibrations, does a really good alignment or modeling of what's really happening with the camera lens and the image plane, but it doesn't model it exactly. And those imperfections in the modeling process introduce those the jitter that you saw. So how I get around that is I use manual labeling. So I take the points in the virtual world, I just select points on the three-dimensional model, and because we've performed a digital twin alignment, it aligns really nicely. I then take those three-dimensional points, just like we saw earlier, project them into the image, as you see on the right, and then I go into software, manual labeling software like RoboFlow on the right, and that allows me to generate accurate labels. And because the probe in the foreground doesn't move, throughout, because the camera is attached to the probe, it doesn't move. Then I can use actual, like real imagery to label that probe. All right, so the final technique is virtual projection labeling. This produces virtual images of the drogue. This is the same exact procedure we used in study 1. So techniques 1 and 3, those are drogue labeling techniques, and then labeling technique number 2 is my probe only. All right, so now I'm going to get into scene augmentation. How did I actually augment the scene? That is the background, the lighting, and perspective. So I started by trying some green screen techniques. There's an app on the App Store called Green Screen Plus Background Editor, and that allowed me to remove the green. And then I had to use software like Photoshop to remove the rest. The problem here is we still have some artifacts within the drogue, and in order to get those out, it's very time consuming. And I needed this approach because we have to generate tons of training data in order to make this work. This was not going to be sufficient. So what I tried next is a technique that I call reverse green screening. And so I take the virtual object, virtual space, and I update its ambient, diffuse, and specular to solid green, and that results in the image in the center there. Then I can use traditional green screen techniques. In this case, I just applied the Vlahas algorithm, as shown at the bottom, using the virtual image in the middle as the foreground. So traditionally, that would be the background, and you'd have a green screen on the real image on the left. In this case, I greened out the drogue and use that as the foreground, and then I take the real image on the left and use that as the background. When I merge them, you get what you see on the right. So here's just a video that describes or shows that process. So I change the object in the virtual world to green, and then I do the Vlahas algorithm. It has an alpha 1 and alpha 2 components, and when I vary those, this is what you see. And so this allows me to do the scene augmentation that I need in order to train models. So right here I'm showing shadow effects, glare on that drogue. I'm moving it. That's perspective augmentation, and I'm changing the background augmentation. And this is what leads to better model generalization and performance. So in addition to blending virtual and real imagery into hybrid imagery, I also have to blend drogue imagery with probe imagery. And I just, in order to do that, I just use a simple alpha gradient masking. So I take the mask on the left, that looks like this, and then I do and if you look up close, there is a gradient along that line. So white pixels correspond to what I carry forward on the probe foregrounds, and then black corresponds to what I carry forward on the drogue backgrounds. So there's one problem that I ran into when generating random positions of that drogue, and that is that I sometimes ran into images like this. When I blended the probe foreground into the image, I completely lost the drogue. And so when I labeled that, you see that it's completely occluded. And this is not what I wanted to train the neural network, because it would get confused because it doesn't actually see a drogue. So what I wanted to do is to actually see the drogue, and from what it sees, it finds. So in order to solve this, I just I applied the point and polygon algorithm. So I defined points along the outer silhouette of the probe, and tested if points were in that polygon, and if they were occluded, and if 50% or more of those points were outside the polygon, like this image, then I said that was good, and then I left those labels in. So the labeled images on the left, I completely removed from the data set. The ones on the right, I retained. And then finally, I had to actually do the network, the supervised machine learning, the model training. In each data set, I used 17,800 images, with an 85-55 split. Those are percentages of both probe, drogue, and neither. So if the bottom right 3 images contain both the probe and the drogue, and then the bottom 2 left images contain only the probe, and the top 3 right images contain just the drogue, and then finally the top left images contain neither the probe nor drogue. So those respectively made up the data set of images, of labeled images, of 85%, 5%, 5%, 5%. The rest of the hyperparameters listed here on the left, I just carried forward from experiment 1. And then I took different compositions of that data to generate models that I could test. So this is these are my 3 experiments. In the first experiment, I generated 7 different models using a combination of real, hybrid, and virtual data, as you see in the top right. And here's a visual of what that looks like if you're a visual person. So R corresponds to real, H corresponds to hybrid, B corresponds to virtual. And these are the different compositions of the 7 models that I trained. Then I ran the models using the relative vectoring pipeline, and that produced quantitative results because I could compare them with motion capture truth, and then I show those on plots later in my presentation. I also wanted to verify that moving the camera also didn't affect pipeline accuracy. So I just kept the probe and the drogue stationary, moved the camera to see if it produced the same probe-drogue vector, compared that with motion capture truth for a quantitative analysis. And then finally, I used qualitative analysis on real flight test data to assess generalization and performance. And then I did that by following the same exact steps as we saw before, but instead of replacing or merging in the artificial drogue in the lab, or the artificial probe in the lab, you see that the real probe from the Learjet is in the foreground now. And I use the same process to the manual reusable labeling to label it. All right, so we're just going to take a break real quick to see a live demo of how this looks, and then I'll go into the actual results. All right, for this live demo, I'm going to switch over to my other laptop, and what you see here in the top right is a live camera feed coming from that camera mounted on the back of the probe. And what you see on the left is a digital twin of what's going on inside this room. So those are virtual objects aligned to real-world objects using motion capture data. So I'm just going to pan around the scene here in the virtual world, get a closer look. And what you see here now is a blue vector that tells us the truth. That's coming from the motion capture system, and aligned with a yellow vector, and that's coming from my relative vectoring pipeline using only the image on the right. And so the fact that we see the blue and the yellow vectors on top of each other is really good. So what I'm going to do here is enable the visual of what YOLO sees. So the neural network is picking up all the features in blue here on the right, and from those features, it is able to perform relative vectoring and determine where the drogue is relative to the probe. So what I'm going to do next is just move the probe around. So I'm just kind of pulling the probe back, waving it side to side, and just watch the yellow probe to drogue vector on the left.
And it's jumping around a little bit, but for the most part, it's tracking precisely with the truth. And it's the algorithm is, and then so what we're seeing here is there's some occlusions. The probe just went in front of the drogue, and the algorithm was resilient enough to overcome those occlusions. And so now I'm just going to move the camera around, showing that this algorithm does not require any extrinsic camera calibrations. So you can like orient the camera however you want, as long as it sees the probe and drogue features in the same image, then the algorithm works the same, generates the same vector. Now, as I put my hand in front of features, you see that there are some occlusions happening here, and the pipeline's still working really well at finding that probe drogue vector. I can even stand in front of the drogue and check out that yellow vector. And then if I grab this board over here, I couldn't even cover up enough features with my body, but if I use this board, I can cover up enough features where it will start to struggle. So it doesn't start struggling until maybe it sees like 3 or 4, but as soon as it sees a ton of features, all of a sudden it's very accurate again. And this is what we want. So for the next part of this demo, I'm going to just turn off the lights, and I've got a work light here that I'm going to turn on. And so as I shine the work light on the scene, you see that there's lighting changes. These are changes that you're going to see in the real world, right? As the plane's banking, as the sun's glaring from different angles. I'm washing out the drogue by walking behind it. Now I'm kind of shining the light from different angles, and traditional methods would get completely confused here. In this case, with machine learning, it is resilient enough to find enough features. Even when it starts getting really dark, it accurately finds the features in order to generate an accurate probe drogue vector. So this is what is going to solve autonomous docking.
All right, so here are the actual results. Results are in. Combination training looks like the pipeline is very fast still. I actually used an upgraded laptop in this experiment with a higher performing GPU. So an RTX 4090 GPU, as you see in the center, on a Dell Precision 7680. On the right are the error plots. These are violin plots showing the distribution of error for the 7 different models that I trained. The one in the middle that shows a significant amount of error, that is the virtual only trained model, with the one right next to it, to the right of it, being the highest performing model that had virtual plus real. So virtual only produced the worst results, but then if I added real data to that data set, all of a sudden it produced the best results. And then this is so this is 0 to 1 meter out, 1 to 3 meters out, and then finally 3 to 6 meters out. All right, so combination training results. These are the top 2 performing models. In the middle is my virtual only results. As you can see, the variance and the error is kind of all over the place, whereas the virtual plus real results are very steady, and they produce nearly 0 error at contact, which is really exciting. And then when I move the camera around, and so I got a couple clips to see what that looks like. So in this video, I actually moved the camera around. I moved it position, changed its position and orientation. As you can see, it's producing a very accurate probe-to-drogue vector. This video, I used a different camera. In this case, this has a 3D gimbal on it, or a gimbal for more stable imagery. But it's also producing a very accurate relative vector. And then in this final video, I show this is the results that you see in the plot on this slide. So I'm moving the probe and drogue around, or I'm moving the camera around, not moving the probe and drogue. And you see that here is the histogram of error measurements, with the majority being within the green, the acceptable range. And then finally, we have true flight testing. In this case, I've got over 600,000 images from 8 different sorties, totaling probably 12 hours of flight time. So I'm not going to show you all of that, but here I just highlighted the most interesting. And actually, I'm only going to go into one of these because they were all consistently accurate. So we'll just look at plot C. And in plot C, what we're seeing is level flight, a gradual approach, near contact about 3 meters out. The drogue rapidly sweeps across the field of view and behind the tanker. And so here's the plot. In red is our highest performing model. And the qualitative analysis I'm doing here is testing the variance. So if the predictions are all over the place, like you see in orange, then I could pretty much tell that that's not accurate. But if the predictions are consistent and they're stable, like you see in red, then that gives me very high confidence that this is producing the real probe-to-drogue vector. On the left here, you see that there is an area that's highlighted in gray. That is what you see on the right. I've just expanded it out. The top plot is the magnitude of the prediction, and the bottom is the number of features found on the drogue across a particular image. And so here is just a quick video of what that looks like. So I've got 4 different models trained. You see the model all the way to the left with trained only on real images, does really awful, doesn't find pretty much doesn't find any features on the drogue. Once I added scene augmentation, that same model all of a sudden finds features. And then when I add virtual and real data together, that's when it starts performing really well, as you see here. All right, so flight test results are really good. All right, so what we see here, I'm just going to fast forward to the end where really exciting things start happening. In this case, this is the night flight where the light started going down, started getting dark, and what we're seeing is that the networks, especially the 2 on the right, still find features all over that drogue, despite never having been trained on those green, brightly lit LEDs that are now in the image that the neural network has never seen before, and it's still able to generalize that is the drogue. So these results were really exciting. All right, so to summarize, we talked about how to generate virtual, hybrid, and real imagery using various labeling techniques, as well as scene augmentation and augmented reality techniques. We generated labels, trained models, and then we tested all the different combinations of models to see which one produced the best, the highest performing, and most generalizing results. So here's just a visual of what that looks like. You have the virtual and real images. where I performed a digital twin alignment using fiducial targets on the right and real motion capture data on the left that localized the camera and allowed me to swap out the April tags with real objects, as we see here. And as long as we don't move the camera, that digital twin alignment is still valid. I can then take the virtual image, change the ambient, diffuse, and specular to solid green, then do a blending of the two images using a reverse green screening technique. And then I can project known features that are defined in the local space of that drogue, rotate them into the world space, project them into the image, and then surround those with tightest fitting bounding boxes with bounding box corrections. That gives us our accurate, precisely labeled images, virtual, hybrid, and real. Then finally, we use manual reusable labeling to label probe features, and then use alpha gradient masking to blend the two. And so, as we saw in the results, this produced positive transfer learning that generalized well across varied conditions, also with high performance in real world scenarios, producing results similar to what we saw in study 1. For this work, I have submitted a manuscript to the Journal of Neural Computing and Applications. That publication is currently under review, under peer review for publication. So to conclude, I introduced relative vectoring. We found that it is accurate, reliable, and fast, proven in real-world applications, and generalizes well with high performance. We also saw that scene augmentation is necessary, and so where do we go from here next? A few initiatives we're already exploring on the team. We've got more flight tests coming up this December. Our last flight test, we only had cameras facing up. Next, we're going to also, in addition to facing up, we're going to face the camera looking back at the receiver. And if those two views result in the same vector, then we have a very high confidence that this that those vectors are accurate and reliable in real-world conditions. We're also doing some drone testing at Camp Atterbury, applying these to smaller air vehicles. We've got some initiatives that we're working on to apply this to omnidirectional or fisheye imagery. So I have a quick video that shows what that looks like. One of our researchers, Richard Nyquist, put this together. It's got he actually trained YOLO to find features in fisheye imagery, which is really exciting, because if we can apply this to fisheye imagery, all of a sudden we've got a much wider field of view. We can see behind us, in front of us, and all around us. And then the last thing that we're already that I'm going to show that we're already trying on this team is called pseudo or synthetic relabeling, where Major Choate, who's defending his dissertation here in a couple weeks, if you want to attend to see what he's doing with this, he's taking the imagery on the top left, training a network in simulation, applying it to real-world imagery, and it doesn't do that well. But if you then use these labels to reproject image features, as you see in the top right, then all of a sudden you can train again, you can iteratively train again on new imagery, as you see in the bottom. And then Ryan Radig, another guy on our team, he actually applied this to real operational data, which is super exciting, because what we see is that these labels are very consistent and have a really high chance of producing really good relative vectoring results. So some other things that we haven't quite explored or that are on the horizon is applying event-based vision sensors that can um, operate at much higher frame rates. We're also looking at ways to pick out better features using genetic algorithms, and then the list goes on. So those are the ones I just showed you are my favorites. There's so much more work to do, and then that ends my presentation.